Hey folks, so in this module, we are going to be doing the T procedures, specifically a T hypothesis test on the mean and a T confidence interval on the mean. But first, we need to talk about this new to you distribution. So this distribution, called the student T distribution, occurs when we don't have ideal situations. When the population standard deviation sigma is known and the sampling distribution of the sample mean is normal, it has a mean mu and standard deviation over square root of n is the standard error. The test statistic is a z-test statistic that's x bar minus mu over standard error. That follows the standard normal distribution. But most of the time, if we're trying to estimate or test the population mean mu, it's because we don't actually know what the population standard deviation is. And so this thing here, let me get a pen. This thing here, standard deviation, is also unknown. So when we don't know the population mean mu and we don't know the population standard deviation sigma, we use the sample mean and the sample standard deviation as estimators. But because we've added this extra estimator, sigma for sigma, this leads us to a new distribution called the student T distribution. Or it can just be called the T distribution. And I'm just going to write Tdistn for distribution. So this distribution came about because a guy named Thomas Gossett was working for Guinness Beer and he was trying to make a better beer. And I'm just going to keep the story as short as this. This happened in the early 1900s where they were using this different Z distribution, the standard normal distribution, and they weren't getting exactly the results they wanted. And so he and a mathematician developed this new distribution, but they couldn't use their names with it because Guinness wouldn't let them publish. So they did end up publishing, but they published it under the name Student T, and it stuck. So when sigma is not known, which is pretty much always, and must be estimated with the sample standard deviation S, and the sampling distribution of the sample mean is approximately normal, then the test statistic follows a t distribution with n minus 1 degrees of freedom, and that gives us a test statistic that'll look familiar. So remember when we were testing the proportion, we had a statistic minus a parameter divided by the standard error of the statistic. Well, that's that same format we're going to have in this section. It's a t-test statistic, and it is equal to x bar minus the mean mu divided by standard error, which is s over the square root of n. And we're using s here because we don't know sigma. So the properties of this t distribution. The t distribution looks remarkably like the normal distribution. It's bell-shaped, but it's thicker at the ends or in the tails than the standard normal distribution. The t is distributed so as to form a family of distributions, sort of like that chi-squared was. There's a separate distribution for each different number of degrees of freedom, n minus 1. And the degrees of freedom are one less than the sample size, n minus 1. But you guys, this is not always the case. It's just the case for the inference we are doing in this module. T is distributed symmetrically about the standardized mean 0. And the total area under the curve is 1 or 100%, just like it is for any other probability distribution. The t distribution approaches the normal distribution as the number of degrees of freedom increases. All right, so here's what this t distribution looks like. We have 3 different curves, and each of these curves is associated with a sample size, and I'm just going to highlight a couple of them. So when sample size is relatively large, So let's say n is 26 and degrees of freedom are 25. We have this graph that's the tallest and the narrowest, and I'm highlighting it in yellow. Then the smallest graph, when sample size is 6, this graph has more area in the tails, and I need to make this just a little bit thinner. There we go. This graph has more area in the tails and less area in the middle. But notice all three of these graphs look like a normal curve. The difference is they get shorter in the middle and more area in the ends as sample size gets smaller because we had to estimate sample standard deviation. As sample size gets bigger, this looks more and more like the normal, and we don't particularly care if we've had to estimate the standard deviation. Some people will use a different distribution when you have a very large sample size. I use the t-distribution if I've estimated sigma no matter what. So what we want to do in this module is do a hypothesis test for the mean mu. The hypotheses, we've already practiced writing these in a previous module. Our null hypothesis is going to be that the mean mu is equal to a number. And then the alternative hypothesis is going to be that the mean is not equal to a number if we're doing a two-sided test. If we're doing a one-sided test, our alternative is either that the mean is less than that number in the null or greater than that number in the null. The conditions for this hypothesis test on the mean, the data come from a simple random sample. So we have a random sample. And then we also have to satisfy normality somehow. So the data come from a normal population. We would be told this, or it would be a variable that we'd be very familiar with and know historically what its shape looks like. We can look at a graph of our sample data and see if it's reasonably normal. And in this case, we can do a histogram, a box plot, or a QQ plot. And then we can also apply the central limit theorem. So if we have large sample sizes, the central limit theorem applies here when n is greater than 30. So we have to show that we have a random sample of numerical data. We have normality somehow. And by the way, I've given you 3 ways to satisfy normality. There are others. We just don't do them in this class. And then the last one is that because sigma is unknown, we estimate it with S. So we say sigma is unknown, and we're going to use S instead. This is technically not a condition of the test, but I find that it helps students to think through this. And if we have those 3 conditions, we use a t-distribution. When we have a t-distribution, our test statistic is x bar minus mu over s over the square root of n. And I do want to make a quick note that, and I'm going to put this in a different color, that this test statistic, t, is robust to departures from normality and what that means is we just need data that's sort of normal. If we have a peak near the middle, and no major outliers, we're good. This distribution is particularly good when we don't have data that's beautifully normal. And lots of times we don't because we have small data sets. All right, so we're still going to be doing the same 5 steps of a hypothesis test we've done in the previous hypothesis tests. We're going to state our hypotheses. We're going to pull out all the given information needed to calculate our test statistic t. We're going to visualize our data with a graph, and we're going to satisfy the appropriate conditions so that we know what hypothesis test to do. We're going to calculate our test statistic and our p-value using technology only. And then we're going to make our decision to reject or fail to reject the null. The rules are still the same. If our p-value is less than or equal to alpha, we reject the null. If our p-value is greater than alpha, we fail to reject the null. And when in doubt, you use alpha of 0.05 unless you have a different level in your field or you're told differently in a problem in class. Then you're going to state your conclusion about the alternative hypothesis. So let's just work an example. An industrial company that puts waste into a nearby river claims that the average pH of the water within 100 meters of the dump site is 6.8, which is considered acceptable. A local ecologist randomly selects water samples from multiple locations in the river and measures the pH level of each sample. The data can be found in the water samples Excel file. Is there enough evidence to reject the company's claim at alpha equals 0.05? So before we start this test, I'm going to have you guys look at this data. We're going to pull it into R and we're going to answer the questions. What type of data do we expect? How many variables are in this data set? What statistics or numbers do we need? And what graphs is or are important? So we can answer a couple of these. So we know that we're doing a test on the mean mu. So we're actually testing this number 6.8. And so we are looking to see what the pH levels are. pH levels are numerical data, so we expect numerical data. And we'll look at see how many variables are in this data set in a minute. But we're doing a t-test, and to do a t-test, we have this test statistic, x bar minus mu over s over the square root of n. So we're going to need x bar, we're going to need s, and we're going to need n. We'll also need the mean mu, but it'll come from our hypotheses, ho or ha. And then what graphs are appropriate? Well, we have one numerical variable. And so graphs that are appropriate for numerical variable are a histogram, a box plot, or a QQ plot. And when you're looking at this data, you need to show me a histogram or a box plot. I prefer the histogram. So the histogram is preferred. We use a QQ plot when we have small data sets for sure, or when we can't show normality with the histogram or the box plot. But you definitely want to graph you definitely want to graph your data with a histogram or a box plot. I prefer the histogram unless you have a teeny tiny data set. All right, so let's look at our data. I have this data already in R, so I imported my data using the import Excel file. My water samples data has two variables. We can look at these variables. We have the location, and then we have the pH levels. And if I scroll down, we have about 198, it looks like, samples. And so we want to calculate basic statistics. We also want to graph our data. So I'm just going to go ahead and do those things, and then we'll come back and answer our questions and start the hypothesis test. So the first thing I want to do is look at my histogram. So typically I just look at a base histogram. So I do hist and then, the name of my data frame and my variable. Remember that we're graphing the numerical variable. We don't actually care about this categorical variable location right now. So if I run this data, I get a basic histogram, which is good enough to see the shape of the data. If I don't like this, I can look at a box and whisker plot or a QQ plot, but the histogram is good enough. When we do T procedures, we're looking for a peak in the middle, and we most definitely have a peak in the middle, and no major outliers. It does look like there's probably a little outlier here, but it's not far away from the data. So when I draw a smooth curve over this graph, it looks relatively mountain shaped, and that is good enough. Now, if I actually want to graph this data to produce the graph to show somebody, which I would do if I were doing a hypothesis test, I would need to use good graphing skills. So I went ahead and redid this code separately so you can see both graphs. So I went ahead and edited my x-axis, my y-axis, my title, my x labels, all of those things. And you can see this graph in purple. And then the original graph where I was just looking at the shape for normality. So the reason I do this first histogram is if I don't have normal data, I have to then look at a box and whisker plot or a QQ plot. And if I can't satisfy the condition of normality somehow, I don't actually work this problem. So I would just stop. I wouldn't make a pretty graph then. So I'm making a pretty graph. Now I want to calculate the statistics I need for my test statistic, which are the sample mean, the sample standard deviation, and the sample size. And I've done that using the mean function, the standard deviation function. And to count the number of data I have, I can either go and look at my data and just scroll down, there are 98, or I can use this function length. The length function gives me my sample size. Now we're going to talk about the output here in just a minute. Let me go ahead and run it. Run that data. And those variables show up in my environment on the right. The mean is 6.686. The sample size is 98. Notice it gives it an L. It tells you that's the length or number of data points. Do not keep that L when you report that sample size. And then standard deviation is 0.24. Let's go ahead and go back and start working our problem and answer some of these questions. So how many variables were in our data set? There were 2 of them, and they were location and pH level. And the one that we're interested in is pH level because it's the numerical variable and the one we're actually testing. So let's do this hypothesis test. This is going to look like the other hypothesis tests you've done in the past, you guys. Same steps. We're just using a different test statistic, which changes the conditions and the given information. It also changes how we write our hypotheses, but it feels the same. So our hypotheses are the null and the alternative. And in this module, we're testing the mean mu. So we're testing what the population mean is. So the mean mu is supposed to be 6.8. And if the pH level is too high or too low, that's a problem. So we're testing that the mean is not equal to 6.8. Our problem doesn't actually tell us that. All it tells us is there enough evidence to reject the company's claim that it is 6.8. Well, the opposite of 6.8 is not equal to 6.8. Our given information for our test statistic we need are X bar, N, and S, all of which we calculated. These all come from our R code. So X bar was 6.686. N was 98, and remember, get rid of that L. And then S is 0.24. And the other thing that we're going to need is our alpha level. We are actually told to use alpha of 0.05. You don't have to write it down here. Some people will, some will not. It's okay if you don't. And then our conditions that we need to satisfy to do a t-test are random sampling of our one numerical variable, normality, and sigma is unknown, so we use S. And so we are told that they did a random sample, so we're told that, and we know it's numerical data, we already looked at it. So that condition is met. Normality can be met with the central limit theorem because n is greater than or equal to 30, or from our graph because our graph is sort of mountain shaped. So normality is met for either of these ways. You just have to pick one of them. You don't have to do both. And then sigma is unknown. We are using S. We were not given sigma. You cannot calculate sigma from sample data. You can only calculate sample statistics from sample data. So the next thing we have to do is actually graph our data, and we did that. And we would include this graph from R. You would include the actual graph. So you'd include your good graph here. I can't import that into OneNote, which is what I'm using, so I'm just going to quick sketch it. It looks something like this. And so our graph looks something like that. We would include the actual one. Notice that there's a peak in the middle and no major outliers, and so that's why we have normality. So we have met the 3 conditions for a t-test. And so we can go ahead and use R to do our t-test on the mean mu. And so we are going to be using R code again. So we're going to go back to R. And we're going to do this test in R. So let me go back to R and show you what the code looks like. So now we're going to do the hypothesis test. And let me highlight these comments first. So you may be using either a data frame and a variable, which is what we have, or you may have put a column of data into R. And if that's the case, you use your vector name, whatever you named it. So when you do that, you use the t.test function and then either your data frame $ variable or your variable name, then a comma, then your alternative is equal to, and you choose whatever your ha was. It's either less than, greater than, or two-sided, and you have to know which one you've written down. Then a comma, and remember that less, greater, or two-sided is in quotes, just like it was with the proportion. And then your comma, and then you say mu is equal to whatever the number in the null and the alternative is. So for our example, we have t.test. Our data frame name is water samples, and our variable is pH levels. Notice pH levels has a space in it, so I do have to have quotes. I didn't actually type any of that. I started typing water samples, and it popped up with the data frame name. Then I did my $, and it popped up with the 2 variables, and I just picked pH level. Then comma, alternative equals, two-sided, 2-sided in quotes, comma, mu is equal to 6.8, and I'm going to run that code. When I run that code, I get my t-test statistic. My t-test statistic is negative 4.6568, or about negative 4.66. My degrees of freedom is n-1, which is 97, and my p-value is 1.02 e to the negative 5. That is all I need for the test. You should double check. I did a 1 sample t-test, and the alternative is that the true mean is not equal to 6.8. You should always double check this alternative that it matches your ha. I did have a not equal to alternative. I did have 6.8, so that all looks right. And I'm going to write all of this down. So my t-test, or my t-test statistic, was negative 4.66, and my p-value was 1.02 e to the negative 0.05. And remember that scientific notation, and negative 0.05 means move the decimal place to the left 5 places because we're dividing by 10 5 times. That's 0.0001. Or approximately 0.000. Typically, we round to 4 decimal places. So what does this mean, and where does this come from? You guys, these numbers here come from the t-distribution. So this t-distribution, and this is just the x-axis, the t-distribution is relatively normal because we have a pretty big sample size. The mean mu has been standardized at 0, so we're just counting the standard errors, just like we did when we tested the proportions. So the difference is, instead of only having 3 standard errors showing up on the screen, we have more than that in a t-distribution. 1, 2, 3, 4, 1, 2, 3, 4. And for our example, our t-test statistic is negative 4.66. So negative 1, 2, 3, 4, negative 4.66 is out here somewhere. And so our p-value is associated with the area below that. But remember, when it's a two-sided test, we have to take the absolute value of our t. So that's 4.66 up here also. And so our p-value is also associated with that end. But those p-values, or those areas above and below the test statistic, are so small that they're almost zero. And so what that means is that if our mean, mu, is 6.8, or 0 standard errors away from itself, our sample is so unlikely that it effectively has 0% chance of occurring if the mean mu is 6.8. And so that's when we go to our decision. And remember, our decision, our p-value, is made when we compare to alpha typically. The p-value is 0. And alpha, no matter what it is, 0 is going to be less than that. And we're going to reject ho. And then our conclusion is always about ha. So if we rejected ho, I'm going to cross it off. We reject it. If we reject it, then there is evidence for ha. So there is evidence. And because our p-value is so small, I'm going to say at any reasonable alpha level, because our p-value is basically 0, to show that mu is not 6.8. And what that means is the company is wrong. And the river is unhealthy. Now, what we don't know is it because of the dumping into the river? So we don't know exactly where they took these samples, so we can't say that. The ecologist would probably have done an experiment to study near the dump site, above the dump site, and below the dump site. And if above the dump site is healthy and below the dump site is not, that's a problem. All right, we're going to start there. We're going to stop there, and we'll do the next set of notes in another video.